So this is about ocean energy. So the planet has a lot of oceans. It's a blue planet because of all the water that we got. And that ocean have three kind of energy that we can harvest actually. Thermal and potential and kinetic energy. And we'll see how people can use all those three to generate energy. The problem with all those systems is the dollar per kilowatt hour. Okay, so those systems may be expensive unless you have special cases that make the price comparable to what you will get from burning fuel. Okay, so the first way is thermal. So where is the thermal coming from? It's coming from the fact that the sun is heating the top, and that at the bottom will remain always cold because it's actually very dark too, right? Because the radiation does not penetrate. So as a result, you have temperature difference, right? And you don't have to go all the way to the bottom of the ocean to find this difference. So he's basically saying within 1 kilometer, you could end up with from 27 to 4 degree difference. So that's 23. And as mechanical engineer, anytime we see temperature difference, what should we think about? If I tell you the kitchen in our place is like always very hot, it's like 80 degree, and the rest of the restaurant is like always like 65. So 85 in the kitchen and 65 in the what should you do? Huh? No, that's not circulate. Why? No, we don't want to cool the ocean. We don't.
We want to get hot water out of this.
So anytime here that if you are designing a Hummer, a new big tank, and the tank basically the engine is super hot, okay, and the cabin is very cold. That temperature difference, what would you do with it? You can generate power out of it. That hot radiator could be your boiler, and that could cabin or the air cooled could be your condenser. And so you basically just have to build a small steam power plant, and yes, the temperature difference is not that much, but there are fluids that would boil at the radiator temperature and would condense at the air temperature. And so you can basically have a small power plant on the tank that will generate energy just from that temperature difference. Okay, and so that's what they basically thought over here. If the ocean surface is very hot, not very hot, 27 degree hot, and the bottom is 4 degree, I could put a steam power plant in here, a Rankine cycle. And so this become basically ocean thermal energy conversion, OTEC. Okay, so in the multiple choice sometime I'd say, is this plant is OTEC or like a Rankine cycle, or so you need to remember this acronym. So now why this is sound like not really a great idea? You're like, no, I'm not gonna do this. Why this sound not appealing to you? It's not much, and as a result, because the temperature is not much, if you calculate the Rankine cycle, the Carnot cycle, which is the best ever, like we will never hit the Carnot cycle, right? Which is like what, 1 minus T cold over T hot. That, based on the 20 degree thingy that we just calculated, will end up being 7% maximum ever. 7% maximum ever. That's the Carnot cycle. So our cycle using Rankine cycle will end up being what, 3%? So that sounds horrible. But what is not horrible is that the 3% efficiency is running out of free fuel, right? Which is the sun, and it's always there. And also what's nice is that there is a huge amount of water. This is not like just like one pipeline of natural gas coming. No, you got the whole ocean, so you can pull as much water per second as you want, as much hot water as you want. It will never finish. So if this thing is built on a really big scale, This can generate a lot of energy, yes, at 3%, but 3% of free energy. So then the bottom line to judge this system is not the 3% efficiency. The bottom line is how cheap can we build such a system. Eventually, what is the dollar per kilowatt hour? Okay? And also the fact that it requires 20 degrees C, that doesn't happen everywhere. There's only few places in the world where you will get that much difference. And you can see those places are near the equator, basically. Right? So why? Because the sun is the hottest in this place, so then you can get that big difference. Right? So those are more than 24%. And so that's why actually China contracted Lockheed Martin to run the calculation or the model for how we can build one of those stations near China, basically, to harvest the energy. And there was an experimental one that was built in Africa by a French company. Where Africa? Over here. Okay, so people are actually considering this seriously, right? But it's the cost per kilowatt hour, and also the fact that it's sitting in the ocean, and you know how corrosive the water of the ocean is with all the salt, that make the station basically live in very bad condition, that make it basically short-lived. But anyway, how do we actually harvest that energy? There are two systems for doing this. Let's go to the easy one first. So the easy one, and that's what you should expect in basically a tanker or a heavy armored Humvee or something. It's a closed system. So closed OTEC, closed ocean thermal energy conversion system. What is a closed system? There is a fluid here, working fluid. That fluid could be propane, butane. Actually, there was this one paper here that said if I want to build a 15 kilowatt closed system, what liquid should I use? It's not gonna be steam, but it could be all those things: ammonia, butane, isobutane, and they tried all those fluid, and they figured basically that for different pressure, this would be the cycle efficiency. You can see it's going from 1% to 5%. Yes, temperature difference is small, but the point is that with different working fluid, you can run at different pressure. Okay, and so it would be nice to run at lower pressure rather than building things to be very heavy and big pipes to take the big pressure. So a closed system like this will give you the freedom to pick what thing I want to use. Okay, could be something toxic, it could be, since it doesn't really leave, I don't really care. Alright, and so then that Rankine cycle that have a boiler and a turbine and a condenser and a pump, that's the basic Rankine cycle, right? Does anyone remember the Rankine cycle? So on a TS diagram, how does the Rankine cycle look like? Here is the boiler pressure, and then it expands in the turbine, and then it cool in the condenser, and then you pump to the boiler pressure where it basically go again. Right? So one. Ben is not collaborating today. But anyway, it goes from the boiler to the turbine to the condenser to the pump. Right? Boiler to the turbine to the condenser to the pump. So the condenser and the boiler are simply two heat exchangers. One of them is using the hot water from the surface to heat our fluid, and the other one is using the cold water from the bottom of the ocean to condense our vapor. Okay? So that is a closed open system. Now the other a little bit more complicated system is the open. And what do you mean by open? We actually let the seawater go into our turbine. So how does this work? You get the warm seawater over here and it's water. So on a TS diagram it will exist to the left or to the right of the TS diagram. Where would water exist? Liquid water. Left or the right? Left. It has to be here. This is 1. So point 1 over here is the incoming seawater. It's hot, 27 degree. That's pretty good. But I don't use water in the turbine. I need steam. So they need to send this water into a flash chamber, or using a vacuum pump they need to reduce the pressure on it. So if you reduce the pressure on the water, what happened? What happened when I open my Coke, which is under pressure? When I open it and suddenly the pressure dropped, what happened? Gas come, boil basically. Well, in case of Coke, it's the dissolved gas basically come out. But for this scenario, if you reduce the pressure small enough, the water will boil. And by this process called constant H. It's throttling, constant H. So H1 and H2 is the same. So this point 2, what does it mean that you are in the wet region? When I say that you are here, remember this is the liquid side. We call it subcooled liquid, and this is the superheated vapor, and this is the wet region. So when you are in point 2 like this, or like here in the middle, what does it mean that you are here? You are a mixture. Some are vapor and some are liquid. And you judge how far you are to be all vapor by something called quality X. So if X is 0.1, that means how much is vapor? 0.1. The vapor is a fraction. If the quality is 1, all of the stuff is vapor. Okay? So 0.1, which like this look like 0.1 to me. So 0.1 means that 90% is liquid and 10% is vapor. Okay, so the quality is how much m dot vapor over m dot total. It goes from saturated liquid to saturated vapor. Correct. But the point is, you can see now, if we flash not just to this 2, but we flash all the way to this, we will get what? More and more vapor. So great, a lot of vapor to go to the turbine, but if we evaporate them all the way up till here, the turbine doesn't have any lower pressure to, like there is no pressure to expand to, because we eventually have to expand to the condenser pressure. So we expand from the turbine inlet to the condenser pressure, from the turbine inlet pressure to the condenser pressure. So that limit of 27 degree is a problem, because I don't have that much room. So I need to drop a little bit to generate steam. And then once I generate steam, then I need to expand in the turbine. So one could suggest to me, I can solve this problem by doing what? How can I increase the amount of work that I can get from the turbine? Huh? Go more deeper. You wish that the condenser pressure can go lower. But why the condenser pressure is sitting there? Why he cannot get lower? What is limiting the condenser pressure from dropping a little bit more? Give the turbine a little bit more freedom. Huh? It is water, the cold water, correct. The condenser pressure is set by the condenser temperature, and the condenser temperature need to set on top of the coldest thing that's cooling you. The cold water that you are bringing from the bottom there is the one that you have to set on top of it because it's cooling you, and that's what prevents you. And that's why in the summer our own power plant, when the air gets hotter, the condenser needs to set on top of it, and so you increase the pressure of the condenser, then the turbine does not have room, right? So you wish you can go down, you wish that cold air get down, right? So, but again, that small amount of work that you get, because you don't have that much difference between H and H, between H2G and H3. They are very close to each other. That small specific work is compensated by the large M dot that you can run in that system. So the work, the megawatt or the kilowatt that you are getting from the turbine, 100 kilowatt, is not just delta H. It's delta H multiplied by M dot. So that M dot could be really big because you have the whole ocean. So you can make the pipe really big and you can put a lot of M dot in so that you would have 100 kilowatt out of this thing, even with this much small delta H difference. Okay, so now how much M dot is coming over here? Is it the whole M dot 1 that we are pulling from the ocean? No, only X, only the quality of X2. So X2 multiplied by M dot 1, X2 multiplied by M dot 1 is the M dot that's going to the turbine and then going to the condenser. So if you want to increase that fraction, what do? You have to flash even more, but you flash even more and you are eating from the specific work that you have over here, right? So does this sound like a good problem to have? What is the optimum flashing pressure? Is this an optimum? Should we just like drop to until the quality is 0.1, or should we go to 0.2, or should go to 0.3? How deep we should go? 1 year, the design project of the course was about the cycle and about how to increase its efficiency. And what's your name again? Huh? Rodette? So that was when he said that, when I asked how you increase this work, and he said, well, you can take this down. But I told him I cannot take this down because what Howard just said that it needs to sit on top of the turbine. Sorry, you said you need to sit on top of the temperature of the cooling liquid. One group actually managed to go down than the cooling water. How did they do that? So the cooling water is sitting at 13 and therefore the condenser is sitting at 15. But they said, no, the turbine can go down than 15. How do you do this? Where's the condenser sitting at 15? Can anyone invent that system for me right now? Get a free quiz for it? No, the temperature cannot get lower than 13. This is where our coldest water stuck, and the condenser temperature has to be higher than 13. Is stuck at 15, but still they managed to make the turbine go to lower pressure than that pressure. How did they do that? They wanted to increase the amount of work they can get from the turbine. How do you do it? Free quiz. Does not change the pressure. Forget about the condenser. The condenser is stuck on top of the 13. Condenser is sitting at 15 because he has to be cooled by the 13-degree water.
By expansion.
What do you mean?
After it comes out of the turbine, you can expand and stuff.
How is that done? How do you do that?
Maybe you can condense it, have a larger opening in it.
No, there is a paper already on that system. You should search for it. You will see how did they do this. They make the turbine, rather than just running from here to here, it will go even lower. Okay, you will see. So that was 1 year that was designed. Like I showed them the paper and I told them to analyze the system and basically optimize it after they figure out the equation. What is the optimum position? But you need to see how do those people do it. So maybe that would be a homework problem, like find out the paper that managed to convince or to turn an ocean thermal energy conversion system to operate at pressure difference more than what's available. How do you do this? Because that is obviously a bottleneck in that system. Right. So what are the two equations that we need in that system to solve it? And we need to know that H1 equal H2 throttling. Okay, so everyone remember H1 equal H2. And the m dot going to the turbine is X2 multiplied by m dot 1. So how do I calculate X2? See, this is by definition. X2 over here is saying X2 is m dot turbine over m dot hot water. Sure. Now how can I calculate X2 so that I can calculate m dot turbine from it? Can anyone help? How can I calculate H2? Sorry, X2. How do you calculate the quality? Enthalpy. How? You compare the H2 with the HG and HF, right? So basically, doesn't work out. So Eric is saying the X2 should be H2 minus HF divided by the whole thing divided by what? HF, HG minus HF, and in some book they call it HFG. So it's basically, that equation is basically saying this much divided by this much is our X2, right? So H2 minus HF divided by HG minus HF. That will be your quality, and from that you will be able to calculate m dot, right? That the other part we need to worry about is that if in order to calculate the work of the turbine, it should be H3G minus H. It should be H3, not H3S. But H3S is the easiest to find because it have the same S like H2G. So once you are here and you got your H2G from the table, the same table, you would say that entropy is the same as that entropy. And once you have that entropy, then you know its quality from the same equation. What equation? If I want X3S, what should I do? This S minus that S divided by the total S. You get the quality over here. So you can get S3S, I guess. That is going to be equal to S2G, and then from that you can get X3S from the S3S minus SF, the whole thing divided by SFG. Okay, now once you know the quality, you can get the entropy of 3S from HF plus X 3S multiplied by HFG. Okay, make sense? So I'm saying the quality, you will get the quality from saying this S is the same S, I got the S here, S minus S divided by the total S at those two temperature will give you the quality. Once you have the quality, you can get the H exactly the same way. The H here is the HF plus X multiplied by HFG. So now this will allow you to calculate the work ideal. This H minus this H. The work actually is smaller by how much? By the isentropic efficiency. So one could say that the work actual is gonna be the work ideal multiplied by eta of the isentropic efficiency of the turbine, and that work ideal is gonna be H2G minus H3S. Okay, H2G minus H3S. Okay, so you got work ideal, you multiply by an efficiency and it become a little bit smaller, and you will get this H in case you know you want to know how much heat transfer is going through the condenser. So in this example he said determine the system efficiency and the warm water and cold water and the turbine mass flow rate. So because he want to know how much cold water is coming and how much hot water is coming, you need to know those Q's. Okay, so you need to know how much Q dot is going into the condenser too. So now the condenser are two kinds. There are two kinds of condenser used in this system. There is a closed loop condenser, and there is kind of an they say it basically open contact condenser, where they spray the water in the incoming cold water. So you need to apply the first law of thermodynamics to find out how much M dot cold water is coming. And the bottom line is that when the steam is going from 3 to 4, the cold water is coming from 5 to 4. Okay, so this much heat lost from the steam is going to be gained in the cold water. So M dot steam multiplied by H3 minus H4 is equal to M dot cold water, H4 minus H5. And that's how you calculate M dot cold water. Okay, does this make sense? Q dot equal Q dot. Whatever you lose from here is gained over there. Alright, and so the whole solution is written for you over here and with the number over there. Okay, and the book just had a wrong some number here. I fix it for you so you can read this at home, and you can see how he's calculating M dot water, and he's gonna calculate how much M dot cold water and how much M dot hot water too. Okay, this is the equation that we just wrote. M dot cold water multiplied by H4 minus H5 equal M dot turbine or M dot steam H3 minus H4. Steam is doing 3 to 4 while the cold water is doing 5 to 4. Okay, I think really the hardest part is this flashing thing, that how the H1 is equal H2 and how we can calculate M dot steam out of this quality too. But the rest is a simple Rankine cycle that you guys did before, and we know what's the efficiency, right? What's the efficiency? If I said what's the efficiency of the system, how do you calculate that? Work net divided by Q added, right? So what is Q added in that system? What will be Q added? So work actual is basically the work turbine, right? Minus what? Minus this vacuum pump work, minus this cold water pump work, right? So you will see that he will actually neglect those, and he's right in neglecting them because the pump work is very tiny compared to the turbine work. And the same thing over here. So he will neglect those guys, and he will think always, like throughout this chapter, that the work net is mainly the turbine, and forget about the pumping work. Okay. So I'm also saying that you need another pump over here. So that pump is the one, because the turbine is under vacuum, or the exit of the turbine, and the condenser is under vacuum. Then you need a pump over here. Okay, but again, this pumping work is very little. It takes very little energy to pump water. This one is taking you from vacuum almost to seawater or atmospheric pressure. But you will not see all those guys in the calculation. You will basically just neglect them. Okay, and then the question is, what is the Q added? So he's saying H3 minus H4. Okay, and when you do H3 minus H4, that is 3 minus 4. That is not Q added. Okay? So it should be H2G minus H4. That's what we deliver to the system. We give him basically H2G, and we receive it from him at H4. So this is how much energy we give it to him, and this is how much work we are getting from him. Does this make sense? Okay. So think of it like we give you back the H at 4, and you give it to us, to the turbine, as H2G. So from here to here, I'm looking at this and I'm thinking this is my boiler. I give you the water at 4 and you bring it back to me at 2G. Okay, so that is the Q added. And especially that this part of the cycle requires the same m dot, like the m dot going to the turbine. So then it makes sense that m dot is cancelled. So m dot is cancelled because it's the same m dot going through the turbine and m dot going through the boiler. Okay, when you read this back at home, it will make absolute sense. All right. Okay, and we are done. Thank you so much.